Hi, this is Professor Fernandez, and in this video we're going to work out a couple more examples of the ratio test, this time with series that involve factorials. These two examples come from the lesson notes from lesson 10. You can find those on my website where you'll find these other resources as well. So, ratio test with factorials. First thing I will do is send you over to video 10.1 for a review of the ratio test. I'm going to zoom in here real quick. You can pause the video if you'd like to read the actual test itself. But video 10.1, I go through that theorem, give you some tips and details about the assumptions of the theorem, and then work out 3 examples of each one of the 3 cases in the theorem. So check out video 10.1 if you're looking for that sort of first entry into the ratio test. I'm going to assume that you've done the ratio test before, and maybe not have done it in the context of a series with factorials. So that's kind of the point of this video. Okay, so first thing to know is that factorials, right? What are factorials? In this class, we covered them in lesson 3. So you can head on over again to the website to download that lesson and see the official, if you will, definition of factorials. But long story short, 3 factorial, let's just do an example here, is the number multiplied by all the quote whole numbers down to 1, right? So this would be 6. And 4 factorial would be, same thing, the number multiplied by all the whole numbers down to 1. So that's 24. And then one thing you notice just writing this out is that this 3 times 2 times 1 is 3 factorial. So we have this nice property that 4 factorial is 4 times 3 factorial. And if then I just generalize this, I take any number n, factorial is going to be that same number n multiplied by n minus 1. Okay? We sometimes see this in its plus 1 form. So if I start with n plus 1 factorial, then it's that number times 1 minus it factorial. So this is a core property of factorials that we're going to use over and over again, and especially when we start doing ratio test in this video. So let's talk about this example with the ratio test with a series involving factorials. Remember from the ratio test and from that video 10.1 that what you want to do is, first of all, pick out the a sub n of the series. And I would again suggest that you take the entire expression, even if it has -1 to the n, making it an alternating series, or whatever it has, just pick out the entire thing as a sub n. So that's 2 to the n over n factorial. This particular series does not have any zeros in it. One thing to know is that 0 factorial is defined as 1. 1 factorial is also 1. So, the first term here, n equals 0. 2 to the 0, that's 1. 0 factorial, that's 1. So the first term is 1. Why do I pause to remind you about the importance of zeros in the series? Because in video 10.1 we talked about how that was one of the assumptions of the ratio test. In that video we also talked about how to get around those assumptions if a series has a finite number of zeros. So check out that discussion in that video if you're interested. All right, we have our a sub n here. It does not have any terms that are 0. I'm next going to write down a sub n plus 1. So everywhere I see an n, I'm going to put an n plus 1. And notice already for our later benefit that there are things we can simplify here that we're going to do that simplification right now. So 2 to the n plus 1, that's 2 to the n times 2 to the first, right? Same base at the exponents, rules of exponents. And then next, the denominator is n plus 1 factorial. So if you go back a minute or so in the video, we had talked about this property, right? So we're just going to slot that in here. So n plus 1 factorial is n plus 1 times n factorial. Great. So we have an, we have an plus 1, so we're off to do the ratio test. We now construct the ratio of successive terms and its absolute value. We're not going to need the absolute values because these terms are always positive, these terms are always positive, so we don't need the absolute values. So this is an plus 1, so that goes in the numerator. And we are going to divide by an. Here's an, so that's the same as multiplying by the reciprocal of an, so n factorial over 2 to the n. Okay. And then you can see lots of things cancel, right? So the 2 to the n's cancel, the n factorials cancel. So what's left is 2 over n plus 1. Great time to go back and talk about the intuition that I also mentioned in video 10.1 about a series, and you can kind of tell whether it's going to converge or diverge. You shouldn't conclude for sure. You should apply a test, but you can kind of tell just by looking at the terms. 2 to the n exponential function goes to infinity very quickly. However, n factorial, like we learned in lesson 3, we talked about it then, and also lesson 4, those are the notes I'm referring to, factorials grow even quicker than exponentials. So we expect that this is going to converge the series because 2 to the n over n factorial goes to 0 pretty quickly. Okay, so here we are. We have the ratio of successive terms in absolute value. And now the ratio test says take the limit as n goes to infinity of that quantity. This one is is much more straightforward limit than what we've been doing in the previous few lessons, because if you graph this function, basically it just goes to 0. Let's see, at n equals 0, it's 2, and then it just decays, right? So this goes to 0, and now we take that conclusion and we compare it to the 3 cases in the ratio test. 0 is definitely less than 1, right? So the series converges absolutely. Remember, that means that the series of absolute value terms converges. Again, for our example, that is the same series that we started off with because all the terms were positive, but nevertheless, it's pretty strong convergence. Okay, so that's part A. Let me actually remove all of this stuff, make room for part B. So let's check out part B. So zooming in here, part B, different series, and speaking again to this idea that we talked about in the previous video, that there may be more than one test that you might want to apply or might need to apply, right? The ratio test does have a case where if the limit of the absolute value of the ratio of successive terms is 1, the test is inconclusive. So that means go off and apply another test. This series is an alternating series, so already that's another test you could apply. You want to keep that in mind. However, going to the intuition about convergence and the speed of the terms an going to 0, we just in the numerator have a 4, and then we have this factorial that is just going off to infinity very, very quickly, right? Faster than exponential functions. So this term here, the whole quotient, is going to go to 0 really fast. So we definitely expect this series to converge. All right, so let's show it using the ratio test. I'm going to use I'm going to choose an to be the whole thing. There's my an, 4 over 2n factorial. And then an plus 1, everywhere I see an n, put an n plus 1. Okay. And then I'm going to form the ratio of successive terms in a minute. But let me try to simplify what's here. So we'll do a little side calculation up here. 2 times n plus 1 factorial, right? So first of all, it's 2n plus 2, right? So I distributed the 2 factorial. And I'll put parentheses here. And then this is 2n plus 2. Remember how factorials work. It's the number times the number minus 1 times, you can keep going. The number minus 1 again, right, times the next one down, right, plus 2, right, and so on down to 1. Okay, notice that here I have 2n plus 2. This one is 2n plus 1. This one is 2n. And then the rest of it keeps going down to 1. Okay. This part here, I'm going to lump into 2n factorial, because that's what it is, right? The number times the 1 below, times the 1 below that, so on and so on until we get to 1. The rest of it, I'm then going to keep in front this way. Okay. And now stepping back and looking at this, right, it should kind of make sense. We started with the number, 2n plus 2. We multiplied it by one less, right? And then we multiplied that by the factorial of 1 less than that. Okay, so that's what goes down here in the denominator. 2n plus 2, 2n plus 1 times 2n factorial. You might be wondering, that was a little complicated. Why would we do that? The reason is that now, notice that this term appears over here, right? So an plus 1 and an have this term in the same fraction. So now when we construct an plus 1 over an absolute value, those things are going to cancel, and you'll see that in a minute. Okay, so an plus 1 is this term, minus 1 to the n plus 1 over 2n plus 2, 2n plus 1, 2n factorial, divided by an. Here's an. So that's multiplied by the reciprocal of this. So times 2n factorial times, 4 in the denominator times negative 1 to the n. And then remember absolute values of all this. So this series does have some terms that are negative, right? It has a bunch of them. It's an alternating series. But because I'm taking absolute values, I don't even have to worry about simplifying this algebraically. They just go away, right? The absolute value of any terms that have a negative sign in them become positive. So that's nice. And then now here is the cancellation that we talked about earlier. This 2n factorial is over here. They cancel. So that's very nice. So what's left? In the numerator, right, I just have a 1. In the denominator, I have this term, and I have a 4. So 4 times 2n plus 2, 2n plus 1. And again, this is, compared to what we had just gotten from example A, I think we had gotten, I'm blanking already, I think it was 2 over n plus 1. I think is what we had gotten from example A, which went to 0, right, pretty quickly. Compare that to this. This goes to 0 even faster because the denominator is a quadratic function of n, right, with a positive leading coefficient, right? Not that that matters so much, but just to be precise. So this indeed goes to 0 faster than example A, which again is what we expected because here you had this exponential function in the numerator, kind of duking it out with the factorial to see if the quotient was going to go to 0. Here in the numerator, you just have the constant function 4, right? So that's 4, stays 4 forever. So you expect that this convergence is even to 0, is even faster. Okay, so indeed, we now take the limit as n goes to infinity, limit as n goes to infinity of this term. So we'll just duplicate it here. There we go. And because it's 1 over, basically, right, 1 over 2n squared, 2n times 2n, that's 4n squared, times 4, that's 16. It basically looks like this for really, really large n. N goes to infinity. This also equals 0. So last step, as always, we compare to the 3 cases in the ratio test. And once again, we obtained a limit that is less than 1. So again, we get the conclusion that the series converges absolutely. So that is useful information in this case, because if I just remove all this clutter, go back to the series, this is an alternating series. Alternating series. Yeah. And we've just shown that the series given by the absolute value of these terms converges, right? That's what it means to converge absolutely, that the series of absolute value terms converges. And therefore, this implies that the original series that we're looking at converges. Why does it imply that? Well, that's based on the absolute convergence theorem / test. Right, so have a look at lesson 8 notes, again on this site, for a quick refresher on what that test is and what it says. Long story short, it says that if the series of absolute value terms converges, then the original series, or whatever the series without absolute value terms, converges. Okay, so that's it for this video. Thanks for watching.